Hello, so this is the second lecture in my mini course on Galois Representations. So let's get started with some math. So last time we saw that actually the Galois group is the automorphism group with a topology. It turns out the Galois group is what we call a profinite group. There are more profinite groups that are going to show up in these lectures and also in other lectures and in the rest of your life. You've probably run into things like this, power series in one variable. Those are profinite groups. You might have run already into the p-adics. Well, if you were at Christel's lectures, then we've seen already the p-adics. The p-adics is an example of profinite groups. Z hat, I forget where my hat is, but Z hat is a profinite group. This is what we call the Tate module attached to an elliptic curve. That's a profinite group. That is all the p power roots of unity. That is a profinite group. And the Galois groups of infinite extensions, those are profinite groups as well. So what is a profinite group? Excuse me. And what is the profinite topology on those groups? Great. So let P be a prime. So here's an example of like how a profinite group works. So for example, in ZP, the p-adic integers, the way I like to think about the p-adic integers are infinite sequences of elements of Z mod P to the N Z. Remember last time we were trying to build what would be the Galois group of the entire cyclotomic extension, the P cyclotomic extension, and those groups appear naturally in that context, and you don't want to do the direct product of those groups. You sort of want some structure that sits on them. So you want this group, the Z mod P, and then Z mod P square on top, and so on, and just groups with maps down. So those are those projections that map from one down to some other one. And then what you want is sequences of numbers of congruence classes, but not all the congruence classes. You want them to be coherent. So coherent means that A3, which is modulo P cubed, has to reduce to A2 when you reduce modulo P squared, and A2 better reduce to A1 when you reduce modulo P. So that's what we mean by a coherent sequence of elements in this tower of groups. And when you look at all such sequences, that is the ring of p-adic integers. For example, for P equals 5, here's a coherent sequence, or you have 2 mod 5, then 7 mod 25. When you reduce 7 mod 5, you get 2. 57 modulo, that would be modulo 5 cubed. So when you reduce this modulo 25, you get 7. And when you reduce 7 mod 5, you get 2. So these are coherent and so on. And you can see that these are coherent. I chose this sequence in particular because every element has the property that this square is -1 in that congruence class. So 2 squared is 4, which is -1 mod 5. 7 squared is 49, which is -1 mod 25, and so on. So it turns out that this number works as I, so that Z5 is really bigger than the integers. The integers, by the way, are inside the p-adics. Sort of diagonally is just the sequence that it's the same number all the time. So the sequence for 1, 1, 1, 1, 1 is the integer 1. But this is a number that is not an integer because it actually works as I. It has the property that I squared is -1 in Z5. So I squared is equal to -1 in the 5-adics. So what other profinite groups do we have? So let's define what a profinite group is. Just in the same idea, we want something that will encompass all these groups with maps down to each other, okay? So first what we need is a set of indices. In the case of the p-adics, the set of indices is very natural, very nice. It's just the integers and everything maps down in this direction, right? But we should be creative. There's going to be, imagine just some complex graph of groups, some tree of groups with maps going down, okay? And that will be allowed as a profinite group. So all of those. And if you imagine a tree, you probably have a countable tree in mind, but you have to think about uncountably many vertices in your tree also. Okay, so what about that? So we're going to need first a partially ordered set, so a directed partially ordered set. So those are the indices with some order, partial order, not necessarily everything that's to be comparable to each other, such that when there are two elements in your partially ordered set, what we do want is that there is an element above them. So there's always something above them. There might not be related to each other, but there's going to be something that connects from above. Okay, so for example, when you have the integers and you have that the relation is being divisible by, so that n is bigger or equal to m, if m is a divisor of n, then we do have something on top of any two numbers. We have the least common multiple such that m is below it because m divides the LCM, and n is below it because n divides the LCM. Okay, so we do want in our graphs, everything needs to be connected from above, so that there are no, if some group doesn't connect to anything in your graph, then actually doesn't add anything of value to the Profinet group, and you can sort of just disregard that group and you will get the same structure as a Profinet group at the end. So that's why we want everything to somehow be connected in some way or another. Okay, so once we have the partially ordered sets, the directed partially ordered sets, we also want a projective system, and that will be a collection of groups, one for each index, and then HOMs whenever two indices are related, which is not for all, but whenever you have j bigger than I, if they're related by this, whatever this ordering is, then we want a HOM that goes from jj down to g, from gj to gi, and that I express from j down to I. Okay, with two properties, two simple properties. First of all, I want that, of course, this relationship is reflexive, so I relates to I, and then the map from I to I, from GI to GI, should be the identity map. And if you have a chain of elements that are related, then if I go from K down to J, and then from J down to I, it should be the same map as if I go from K down to I directly. Okay, so that those homomorphisms speak well to each other. All right, so for example, you can take your indexing set to be all the natural numbers under divisibility, which is what I did here. I'm continuing with this example. Under divisibility, if I divides j, then there is a map from z mod j to z mod I. If they are not related like this, there is no such map. There is no natural map from z mod 5 to z mod 3. There is no homomorphism except a trivial hom that everything goes to 0, right? So for example, there is such a map in that case, and the map, a natural map, is reduced mod I. All right, so we're going to take those for our projective system with those integer, or with those residue integer rings. And then the projective limit of a projective system. So in the projective system, there are three things: the indexing set, the groups, and the maps in that tree. And then the projective limit, which we denote with this funky inverse arrow, the projective limit. And again, we usually drop, we don't write that. So usually from context, you know what the indexing set is, what the group and the maps are, or you have to specify it and say with inverse limit with respect to this projective system. The projective system will be just like in the p-adics. It's going to be sequences, but now remember that the indexing set might be uncountable, so it's deceiving to write them like in the case of the p-adics. You don't want to write an infinite vector because that automatically tells you it's countable, the indexing set. So don't do that. But we do think about them as sequences, infinite sequences, one for each index. So that will be an element in the direct product of all the groups, such that whenever they are related, whenever two indices are related, the connecting map is telling you that the J component will reduce to the ith component. So those are called coherent sequences because they all play nicely whenever there is a group on top of a group. If you chose a component here, this component, there may be many choices, but they have to map down to the choice you already made at the ith component. Okay. So again, if you keep in mind the example of the p-adic integers, that's what when I like Christelle said that in her heart P is 3, in my heart a projective limit is the p-adic integers, and that's how, sort of like how I box everything in. Just think of that for projective limits. So in the case of the projective system that we were talking about, the integers under divisibility, my groups are Z mod NZ, and the natural reduction maps, what you get is what we call Z hat, which is the profinet completion of the integers, and they are infinite sequences. For each component is an element, a class of A mod N, such that whenever there is a divisibility, the congruence classes coincide when you reduce down to the factor. Okay, and this is a subgroup of the direct product of all Z mod NZs, but it's a much smaller subgroup because it's just coherent sequences within that subgroup, within that group. Okay, so another one, another way to put the p-adic integers in that same setting is that take the natural numbers under natural order of the natural numbers, so the greater or equal, take the groups to be Z mod a power of P, then there is a map as long as J is bigger than I can reduce from mod P to the J to mod P to the I. And with those maps in mind, the inverse limit is what we call the p-adic integers. They're coherent sequences such that when you reduce to a lower power of P, they coincide. So those are the p-adic integers. Now, our key example of a profinet group is infinite Galois groups. So if you have any field F and F bar is a fixed algebraic closure or some infinite extension so here you can replace F bar by an infinite extension of F, then take the indexing set is going to be intermediary extensions such that K over F is finite and Galois. And the relation between separate extensions of F is that L is bigger than K if and only if K is contained in L. So if you think of towers of number fields, we usually draw them like that, so that we have F, and then we have K, and then we would have L, and then it would go all the way up to F bar, right? So then L is bigger than K because K is contained in L. Great. So that's the indexing set in the projective system. And then the groups for every one of those, because it's finite and Galois, I can write the classical Galwa Theory Galwa group as my group. And then when they are related, when L is bigger than K, the map connecting these two Galwa groups is simply that I can do restriction. This is an automorphism of L over F. K is contained in L, so I can see what happens to the elements of K. So I can restrict my automorphism to just elements of K, and that gives you a map. Hello. That gives you. Oh, for a second I thought I wasn't recording. It gives you a map from the Galois group of L over F to the Galois group of K over F. And now we have all three things: my indexing set with my relation, my groups, and my maps, and that gives me an inverse limit. And that inverse limit is what we call the well, it's going to be the as defined as the automorphism group of F bar over F. But with the topology we're going to put on in a second, the Profinet topology is what we call the Galois group of F bar over F, the absolute Galois group of F bar over F. Any questions so far? I just wanted a sip of coffee. All right, so let's one more example is that when F is Fp, the finite field with P elements, then we know that F bar, the algebraic closure, is actually the union of all the fields with P to the n elements. So I can write that the absolute Galois group of Fp like I just defined it. Okay, the indexing set will be all the intermediary fields. They're all like that. How are they related? This is not always the case that just because n is bigger than m, there is this inclusion. This happens. We're going to define that when this happens. And this happens when m divides n. Okay, so with that in mind, with this relationship, so the divisibility relation between integers is the relation here among these, and the groups are the Galois groups of the intermediary extensions, which is Z mod and Z. By the way, that is generated by the Frobenius automorphism of this extension, and that gives you then that we can construct an inverse limit. That is what we define to be the absolute Galois group of Fp, and that coincides. You can prove that it coincides with the automorphism group, and with the topology, it will be the Galois group. And well, we know what is the structure of this group. This group is isomorphic to Z mod and Z, and we know what that inverse limit is. That inverse limit is what we call Z hat. So the Galois group of Fp bar over Fp is Z hat as a profinite group. Okay, very good. One more example. So what if we want to do the Galois group of the p-th cyclotomic extension, the maximal p-th cyclotomic extension? So here the intermediary groups I'm going to pick are the p to the nth cyclotomic fields. Now you might question that, okay, there's an infinite extension, and to define the way I've defined these Galois groups, shouldn't I know a priori all the intermediary extensions? It turns out that you get the same answer as a profinite group, as this group. You will get the same answer as long as you've constructed enough. If you know enough subfields such that the union or the compositum of all those subfields gives you this field, then this Galois group or this profinite group will be isomorphic to the other one. So what this amounts to is that if I have a profinite group already in mind, I can always add sort of like extraneous maps that don't end up adding more structure to the profinite group. There's ways to make profinite groups sort of like more complicated without actually adding any more elements to the profinite group. Okay, so so if you add sort of like loops to your profinite group, they don't end up adding more elements. So if you have, say, your tower of groups, and then you add some sort of like paths that create cycles, you do not end up adding more elements, because those coherent sequences, those elements going in this direction or going through some other loop, those elements in the limit will end up being representing the same element in those two groups. So you can prove that there's an isomorphism in those two profinite groups. So the upshot is that actually I do not need to know infinite Galwa theory to construct infinite Galois groups before I prove the infinite Galwa theory. There's not this sort of like logical flaw in my argument. The thing is that I can actually define these Galois groups just by knowing enough, because I know that these, if I do the compositum of all of these, I will get this. There's a question back there. Yeah. here. So my indexing is finite fields of p power order. And I'm saying that I'm going to say this is bigger than this if this is containing this. Yes. So I should, you are completely right that this, I should actually write it something like this to say that is my definition of the ordering is that. No, what did I do? I used the wrong tool. Okay, so that is by definition, that's my order in the order I've put on finite fields. Yes. All right. So if I use my indexing set by a known tower of fields that the compositum of all of them give me the infinite extension I want to compute the Galois group of that infinite extension. I know that the intermediary extensions have this Galois group, and the connecting homs are going to be the following. If I go from this one down to this one to a lower one, what I can do is restriction. And also, actually, this restriction map abstractly on automorphisms works well with this isomorphism, because this isomorphism tells me that this is isomorphic Z mod P to the N cross. This one will be Z mod P to the M cross. And it turns out that this automorphism corresponds to just normal reduction map. Okay, that reduction map actually gives you the same map that this restriction. So then the Galwa group, by definition, will be the inverse limit of these groups with this projective system. And these groups are isomorphic to this. So when I do the inverse limit, actually, I get the units in ZP. Okay. Something perhaps for you to prove is that units, this little cross, and the inverse limit commute. Okay. So perhaps. So one exercise here is that the limit of Z mod P to the NZ cross is the same as the limit of Z mod P to the NZ with the cross outside of the inverse limit. You see, those two things are different because I'm taking two different inverse limits, right? So you might want to think about that. Why, if I've already taken the inverse limit, what should be the units there? Or if I first take units and then do the inverse limit, why I should get the same thing both ways. So this, I think this is a nice exercise to just get used to the idea of inverse limits. Very good. So here's another example of inverse limit that I didn't do before. That is useful in the following. So if I take the indexing set to be the integers bigger or equal to 2 with the natural ordering, then I can take Gn to be 2 by 2 matrices in Z mod to the Z mod P to the N, and then maps, which are just reduction maps, coordinate by coordinate. So if I have something mod P to the N and M is lower, then I can just reduce the matrix and reduce every coordinate. What that gives me is an inverse limit of matrices, and this should hopefully, intuitively, it should be GL2 of ZP, right? What we did is actually the inverse limit is sort of coordinate by coordinate. But this is, again, a nice exercise for you to do to check that you understand what limits are and why these two things, this and this, are not exactly the same thing. Here, the inverse limit is outside of the GL, and here the inverse limit already happened into the coefficients, okay? So again, this is one of the exercises. I'll update the exercise sheet, and this is one of the exercises. And basically what this says is, again, the inverse limit commutes with GL2, right? The inverse limit is here first, and if I actually take the inverse limit outside, these two things should be the same. They're not exactly the same as objects. If you try to construct this, there will be infinite sequences of matrices, while this is a matrix where the coefficients are infinite sequences. All right. So Now that we know about Profinet groups, we need to know what is a topological group. So a topological group is just a group and a topological space at the same time. So I have a group, and then I want to put a topology on that group. So the group is a set, and I can put a topology on that set. What do we want? We want this group to have the topology and the group structure to talk to each other nicely. So what you want is that if the operation is a star, we want that the operation is a continuous map. Here, G times G. So if G is a topological group, then you put the product topology on this G times G, and this map should be continuous. And this is inversion, meaning the inverse with respect to a star. The map that sends an element G to its inverse, that should also be a continuous map. And where once you had, then now we can think about groups in a new way. So for example, the reals with respect to addition are a topological group. For example, here in this drawing, this cartoon tells you why addition of two integers is a continuous map. Because if you start with an open R, meaning the reals with the usual metric topology, so if you start with an open set in R, so some ball, so some interval, some open interval, and I send it back through addition, well, that will be all the numbers such that x plus y end up in this interval. So are the numbers such that x plus y is between A and B. So it's the interior of this infinite band. But you can see that clearly that infinite band is an open set in R cross R, in the product topology of the reals. Okay, so that's a topological group. Great. Oh, well, I didn't prove that. I didn't prove it in every case. You have to be a little bit more careful than this. But if you do it for a basis of the topology, then you know it. So basically this, hi Ambar, how are you? Well, of course, we do want topology. The head of my department, Ambar Gupta, put a question up here. Do we want the topological group to be Hausdorff? So of course, we like Hausdorff spaces, but not everything is Hausdorff. We like compact spaces. We like connected spaces. So it turns out that our Profinet groups are going to be Hausdorff. They're going to be compact, but they're going to be totally disconnected. So that is a strange, that is a random thing that happens, but those are the three properties that are actually going to be very useful to us. All right, so one other exercise would be for you to prove that inversion, so subtraction, or like whatever the inversion is with respect to addition in the reals, that is also a continuous map. Here is an example of a topological group. So the triadics with respect to the usual topology on the triadics. So what does that look like? I haven't defined yet what the Profinet topology is, but I'm going to give you a topology on Z3. So each circle in this image is an open set. So I have all of the triadics, that's an open. I have all, these are the triadics that are 0 mod 3, that's an open. That's the ones that are 1 mod 3, and these are the ones that are 2 mod 3. Those are opens in the topology. And then I'm going to zoom in into the 1 mod 3s. And in the 1 mod 3, there is the ones that are 1 mod 9 or 7 mod 9 or 4 mod 9. Those are open sets also. And then I can zoom in into these and I get more open sets like this. So every open or a basis for the open sets are things of this sort. Pick an integer and pick an integer n, a positive integer n, or a non-negative integer n, and then that subset of the triadics, that will be an open ball in the triadics. Okay, and so again, that's a basis of open sets. You can see here that the totally disconnected part comes from the fact that if I have two triadic integers that are not the same triadic integer, if you start looking, if you think about them in terms of infinite sequences, they will differ at some point. So they will differ modulo 3 to the 1,000. But at that point, I can tell them apart. And then what will happen is that in 3 to the 1,000, one will land here and another one will land here. So I can actually disconnect. I can just pick one ball that contains one of the numbers and then take the union of all the other balls where that number was not in it. Okay, or take in here, just take all of these and then all of these also, take the union of all of those. And now I have two open sets that cover up the entire space and disconnect those two elements. Okay, so this is what we say that the three-adics are sort of like it's a Cantor space. It's a Cantor set because you can actually sort of like see it also as like it looks like a Cantor set already. All right. By the way, some properties of open subgroups in topological groups that are very useful. I'm not going to prove these, but there are some properties that are specific to groups and specifically to topological groups and open subgroups in such groups. So the first is that, so we have a topological group, then every open subgroup is a closed subgroup. Okay, so open implies closed always in for open subgroups. And the reason is that if I have an open subgroup, I can do the cosets of that subgroup. And the cosets, it turns out that because you remember that multiplication is a continuous map, it turns out you can use that to show that topological groups are what we call homogeneous spaces, in that if you have an element and you look at all the open sets that contain that element, by multiplication, the multiplication being continuous, I can bring all my opens to the other element, or rather by the inverse map from here to there. But in any case, I can bring all my opens to another element. Okay, so if you look at the topology around a point, it looks the same everywhere. You can see it very clearly here that it will look exactly the same. Whether I did the picture around 1 mod 3 or 0 mod 3, it looks exactly the same regardless. So that's what it means to be a homogeneous space in this setting. So, and what happens is that if I have an open subgroup, then the cosets are also open. And then G minus the subgroup that I'm interested in is a union of cosets, so it's an open in the topology. Therefore, H is closed. Okay, so that explains, just so you have one proof there, that open subgroups are closed. Closed does not imply open, but closed of a finite index, those are open. Because you can also think in terms of cosets that if it is a finite index, then there are only finitely many such cosets I can break up my group into finitely many cosets of H, and then an infinite union of closed is not closed, it may not be closed, but a finite union of closed is closed, and then the opposite is, or the complement is open. So you can prove that closed plus finite index is open. Another when I was talking about homogeneous spaces, what I wanted to say is that since everything looks the same, regardless of where I am in the group, what we do most of the times is just look at the topology around the identity. So we want to know what open subgroups are around the identity. So what open subgroups contain the identity. And those open subgroups actually determine the topology on a topological group because of this property. In any case, every subgroup of containing a neighborhood of the identity is open. So whenever I have an open neighborhood of the identity in my group, then that subgroup automatically has to be open for some reason. And then also that if H is a subgroup of G, then the quotient G mod H is discrete if and only with the quotient topology, if and only if H is open. So these properties happen just to be very useful all the time. So I just wanted to mention those. All right, so what about profinite groups? What topology are we going to put on them? So we have a projective system, our indexes, the groups, and the homs, and then we construct our infinite coherent sequences according to those maps. The topology on G is going to be the following. We're going to put on every GI, we're going to put the discrete topology. So, by profinite, pro means that it's going to be a projective system, means that I want my GIs to be finite groups. That's the key part here. So I can naturally, since it's a finite group, what topology are you gonna put on that? Don't do something crazy. Just do the discrete topology. Every subset is open. Okay. So GI, they will have the discrete topology. The inverse limit is a subgroup of the product group. So put in the product group, put again naturally, put the product topology. If you do anything else than the product topology, then all sorts of weird things happen with those subsets. So we're going to have the product topology there, and then since this is a subgroup of the product, put the induced subset topology on G, and that is the profinite topology. We'll see what that means, but in short, what this means is that the profinite topology is the coarsest on G, such that the projections from your inverse limit down to any component are continuous. So those projections, the inverse limits or the inverse images of opens in GI, those will be a basis of open sets on G. Okay, so let's see what those look like. So in the profinite topology, the open subsets are of the form, take an open set in the product and then intersect it with the inverse limit. What are the opens? What are opens in the product topology? Fix a little element GI in the group GI, and then this is an open. So everything is the big GI, the full group, except that the ith component that I only have one element. This is an open in the product topology. Okay, and these are I think they're a basis of the topology for the product topology. Okay, so now what is going to be the corresponding open in my profinite group? Well, it will be coherent sequences such that the ith component is exactly GI. What does that mean? For groups that are below the ith component, I know that my maps are going to map down and they tell me what the element has to be. Okay, I think I messed up here. These I changed to H's. So these is H and H. So for components that this maps down to, the HOMs already determine what the image has to be. So those fix whatever has to be here. For components here that this component does not map to them, there's no condition. Now, for other components above it that map down to the ith condition, what they tell me, I messed up again. This has to be from above. So the jth component, if it maps down to I need to make sure that it maps down to GI, which is a fixed element. Okay, so those are the conditions. Again, like in terms of the triadics, what this means is that if you fix modulo 27, if you fix the modulo 27 condition to be 7 modulo 27, that tells me what the modulo 9 condition has to be. It has to be 7 mod 9. It tells me what the mod 3 condition has to be, which is 1 mod 3, right? And then modulo 3 to 100, all that it tells me is that if I reduce modulo 27, that number, I have to get 7. That is the ball with the 7 plus 27 Z3. So that is an open ball, and that is what this is doing in general with all the maps of our tree of projective systems. Okay. So this has to be an open, And indeed, it is an open, because in the topology, that is precisely, if this is the projection to the ith component, that is precisely the inverse image of the little element gi, of the set with the element gi in it, which is an inverse image through a projective, through a projection, and that has to be an open. So that is an open, and these two things coincide. Okay? And those are the basis of our topology, are all those, or the sub-bases of the topology are all those inverse images from one component. Great. And that, if you go back to my first lecture, that coincides with what Krul was saying, or what we were saying for the just example of the product of plus minus ones, in that what we wanted were just like plus minus ones everywhere, except a finitely many components, we can have some strange set, but only for a finitely many components. For all but finitely many components, you have the full inverse image. Okay. All right. So here's an exercise. Now that we have a Profinet topology, it better be that it gives you a group topology that makes the Profinet group into a topological group. So why don't you try to show that with this topology, multiplication in the Profinet group, by the way, it is a group, you multiply component by component, and inversion in the Profinet group, those two are continuous maps. And that makes G into a topological group. All right. So here's an important theorem that I just sort of like previewed when the head of my department came in, which is that if you have a projective limit, not profinite yet, projective limit, any projective limit with the induced topology from the product group, then if all the GIs are Hausdorff, then the inverse limit is Hausdorff. If the GIs are finite, then that is a discrete topology, and that is automatically Hausdorff, so we get Hausdorff. If the GIs are compact, then G is compact. That's actually another way of, or a consequence of Tihonov's theorem that says that a product of compact with the product topology is compact. So in particular, if you have the GIs are finite with the discrete topology, those are compact groups, and therefore our product or inverse limit would be compact. And if the GIs are totally disconnected, so is G. If the GIs are finite and you have the discrete topology, that makes the group totally disconnected. So it makes the inverse limit be totally disconnected. So as a consequence of all these, for projective limits in particular, a profinite group is Hausdorff, compact, and totally disconnected. This will have some big consequences when we talk about, for example, Artin Galois representations. Okay. By the way, you might think, okay, these profinite groups are like really weird and like very some very specific way of constructing topological groups. But it turns out that there's something quite surprising that, well, if you have any group that is compact and totally disconnected, is actually a profinite group, because you can write them as inverse limits of G mod their open normal subgroups. So you can always express such a group as a profinite group. So profinite, those properties are actually defining profinite. Did you have a question?
Yeah.
Yeah.
They just follow the core.
Yeah. 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 Correct. Yeah. So the question was, if this is just for a projective limit, do these just follow for the from the properties of the product topology? And the answer is yes. It all just follows. Like, all we are using is that we have the product topology in that product of GIs. Again, if you don't put the product topology in there, you put some other topology, then all bets are off. But yeah. All right. So in particular, Galois groups, well, if it is a finite extension, it's a finite group. If it is an infinite extension, the way we've defined the Galois groups, again, I haven't done Galwa theory yet, so I haven't stated the infinite Galwa theory theorem, but if they are like we define them in terms of an inverse limit of all the Galois groups of intermediary finite Galois extensions, then that is a profinite group, and therefore Galois groups of infinite extensions are Hausdorff, compact, and totally disconnected. Where these actually, if you do intermediary extensions, just finite without the Galois, that forms a basis of open subgroups of neighborhoods of the identity. If you on top request that the field F is finite and Galois, this forms what we call a system of open normal neighborhoods of the identity. And you can actually always, because the Galois closure of a field contains that field. So basically, if you start with an open that is not normal, then you can base extend to the Galois closure, and then you always have inside an open, you have an open normal subgroup that is another neighborhood of the identity. So we can choose this as a system of open normal neighborhoods of the identity, which, as I said before, these systems characterize the topology. It's not just like, okay, so here's a system of opens. If you know a system of open neighborhoods, by a system means that any neighborhood, any open subgroup that contains identity contains one of these. Okay, so this is something one needs to prove, but in any case, they always contain any neighborhood, and an open neighborhood of the identity will contain one of these opens, which are actually normal. Very good. So we know a bit about the topology now, and this is now, so the theorem, which I'm not going to prove, by the way, Keith Conrad, 2 years ago, I think, during the online CTNT, his course was on infinite Galwa theory. So there is a whole course dedicated to proving the infinite Galois correspondence. And this is the correspondence. So first of all, if you have an algebraic Galois extension, infinite, say, but any algebraic Galois extension, omega over f, then first of all, the thing that I define to be the automorphism group, this inverse limit of Galois groups, it is isomorphic to the automorphism group of omega over f. So the automorphism group is, well, automorphisms of omega that fix f as, or field automorphisms of omega over f. You can first prove that this is actually isomorphic to that automorphism group. And not only they are the same as automorphisms, but also as topological groups. What topology? This is a profinite group, so the profinite topology. And the topology we put on automorphism groups is the following. So basically, the topology is the opens are automorphisms that that fix a finite set of elements. So take a finite set of elements of omega that is Galois stable. What that means is that these are elements that are algebraic over f. So I'm going to take all the Galois conjugates. So what that means is if you have an element, I can write the minimal polynomial, look at all the roots, and put all those roots in the set S also. So it's Galois closed, that meaning all the conjugates are in there of every element in S, but just make that to be finite. Then I'm going to write as an open automorphisms of my extension such that automorphisms that fix every element in that finite set. Every one of those for your choice of S bar, that's an open subgroup. And of course, they include identity because identity fixes everything. So the identity is there. So these are open neighborhoods of the identity. And these actually turn out to be normal subgroups. So this is a system of open neighborhoods of the identity that consisting of normal subgroups. And as I said, that determines a topology on all of the automorphism group. And now that I know both topologies, I can compare. I can first prove that these are isomorphic as groups, and then prove that that isomorphism is continuous and the inverse is also continuous. And that gives me that isomorphism as topological groups. Now, infinite Galwa theory, what it tells you is that there is a correspondence between the subfields, intermediary subfields, and closed subgroups of the Galois group as follows. That a field goes to the Galois group of omega over m, and a subgroup goes to the fixed field, the field fixed by H. All right, let me just do one example. So if I have this extension, the p cyclotomic tower, we know that that is isomorphic to ZP cross. So what are the closed subgroups of ZP cross? Two exercises for you in the homework. First of all, ZP cross is isomorphic to p-adic units that are congruent to 1 mod p, direct product, Z mod p Z cross. This actually, what this is the p minus 1th roots of unity. Okay, in the homework, I first asked you to prove that this is mu p minus 1 is all in here and so on. Anyway, there is this isomorphism, and then the subgroups, the closed subgroups of ZP cross will be, well, this is just finite, so just pick any subgroup here, and then cross a finite closed subgroup of this. A closed subgroup of this, well, this is isomorphic to ZP, so you have to know what the closed subgroups of ZP are, and I'm going to ask you to prove that those are of the form p to the n times ZP. And once you have that, then you can do Galwa theory. So for example, if my closed subgroup is just the units that are 1 mod p, then I can try to figure out what is that fixing. Well, the quotient is, so this Galois group here will be isomorphic to the quotient of ZP cross by this closed subgroup. But if ZP cross was this cross this, so if I mod out this, then what I get is the second factor. So this extension has to be isomorphic to Z mod p Z cross, and then you can prove that that is actually the p's roots of unity. Okay, and if you do, if you fix by, if your closed subgroup is just the second factor in that isomorphism, then now the quotient will be 1 plus p ZP, which is isomorphic to ZP. And what you get is what we call the p-adic extension of Q inside the cyclotomic tower. All right, so I will stop here because I'm over time, but this is the whole picture of all those extensions happening at the same time. I'll stop there. Thank you.